How do VAs discover disentangled representations? Imagine trying to understand a complex puzzle by breaking it into smaller, clear pieces. That's what variational autoencoders do with data. They learn to split information into parts that are easy to interpret. A variational autoencoder, or VAE, has two main parts. The encoder takes in data like images or sounds and compresses it into a smaller, simplified form called a latent space. The decoder then takes this compressed version and tries to rebuild the original data. The goal is to make the reconstructed data as close to the original as possible. During training, the VAE balances two things. First, it wants to accurately recreate the input data. Second, it wants the latent space to follow a specific pattern, usually a Gaussian distribution, which is a smooth, bell-shaped curve. This regularization helps organize the latent space so that similar data points stay close together. Now, to make the model discover separate, understandable features, researchers often tweak the training process. One popular method is called the beta variational autoencoder, or beta VAE. It adds a hyperparameter called beta that scales the regularization part of the loss function. When beta is higher, the model focuses more on making the latent space simple and independent, encouraging each part to representing one specific feature, like color or shape. But if beta gets too high, the model might struggle to reconstruct data accurately. So, finding the right balance is key. Some advanced techniques add supervision signals or guidance. For example, guided VAs use small hints to help separate factors like content and style. Others incorporate causal models, which help the VAE understand cause and effect relationships in data, making the representations more meaningful. Disentanglement means breaking down the data into parts that don't overlap much and follow a clear structure. Techniques that manipulate the prior distribution or add constraints help the model break symmetries and make each latent variable independent. This way, changing one variable only affects one aspect of the output, like adjusting the pose of a face without changing its expression. In real-world uses, disentangled VAs can control image generation. For example, you can change the color of an object or its orientation without affecting other features. This is useful in tools like DALL-E or Midjourney, which create or modify images based on user inputs. They relying on these learned representations to produce more precise and controllable results. Having clear, separate factors also makes AI more transparent. It helps us see how different parts of the model influence the output, which is important for fairness and trust. But achieving perfect disentanglement is still tricky. It often needs some supervision or bias in the training data to work well. To sum up, VAs find disentangled representations by organizing the latent space through regularization, tuning hyperparameters, and sometimes guiding the process with extra information. This makes the data easier to interpret and manipulate, opening up many possibilities in generative AI and making AI systems more understandable and controllable.